Linear independence. When we look at a set of vectors, such as this set of n vectors, here I list each vector, right? List them as v1, v2, for example. Yeah. So first vector, second vector, the last vector as vn. So that shows we have a set of n vectors. The independence or dependence of the set of vectors is very easy to define, because if the set of vectors are not linearly independent, then they are linearly dependent. So first of all, maybe it's easier for you to understand linear dependent by using our form. Let's assume the last vector can be written as a linear combination of the vectors listed before this vector. So we assume this very last vector can be represented as a linear combination. That means we can write Vn in this form. So that shows Vn is dependent on the previous vectors in the set. That means immediately, if we write a system, so let's associate this in the vector form. If I write a system, so these n vectors are given, so I can write v1, v2, vn, and then equals 0. So let's assume the coefficient of the vector equation will be x1, x2, xn. So here we just look at a system of this form. It is a homogeneous system in the vector equation form. So these n vectors are given. So if we look at this homogeneous system, if we try to solve this, suppose our last vector is a linear combination of the other vectors, then we know immediately there's a non-trivial solution to this homogeneous system. Because this when C1 is x1, C2 is x2, so we can just find the non-trivial solution. That is when x1, x2 is C2, and xn minus 1 is Cn minus 1. You see? And then if we move this to the other side, that's -1 times Vn, right? So this equals 0. So we can rewrite if I move that term to the other side, then I get a 0. So that shows a non-trivial solution, because this is -1 for the value of xn. Xn is -1. So we see immediately a non-trivial solution, because the weight or the coefficient for Vn is -1, which is non-zero. So we notice a non-trivial solution to the homogeneous system. This gives you the first intuitive example. That means if one vector is a linear combination of other vectors in the set, then that means we have a non-trivial solution to this homogeneous system. Yeah, because we can observe this non-trivial solution. Otherwise, if we have an suppose a non-trivial solution, if there is at least one non-trivial solution to this homogeneous system, that implies a vector is a linear combination of others. So let's assume, suppose this system has at least one non-trivial solution. And we can just say this is a homogeneous system that has at least one non-trivial solution. Maybe it is this coefficient, maybe that coefficient could be any one of those, right? So let's assume Ci is the first weight that is non-zero. Yeah, for example, C2 could be the first weight of a vector that is non-zero, because we try to see what if there's a non-trivial solution. Can that imply linear dependence among the vectors? So if Ci is the first non-zero weight for the homogeneous system, then we can immediately write, we just isolate this term. This is CIVI, we put it on the other side. Because as you can see, in the standard form, right, for the homogeneous system, so this is our n vectors. If I put the n vectors and try to solve this system, see if I have non-trivial solution. Suppose I have a non-trivial solution, that implies there must be a certain coefficient, which is non-zero. So suppose I find a solution which is the Ci, which is non-zero, then we can move that particular vector term to the other side. Then the homogeneous system becomes this. So since that's the first weight that is non-zero, so this negative Ci is also non-zero. Then because it's non-zero, we can divide the number, both sides of the equation. So then the Vi, after we divide the negative Ci, so this will be 1. So this will be 1. So we get Vi. And then every term is divided by negative Ci. Then what we see, we notice that those will become coefficient in front of the rest of the vectors. That shows the Vi will be representable by the other vectors of the set. So that's the representation of for this Vi using other vectors of the set. So that means whenever you have a non-trivial solution, that means a non-zero solution for that homogeneous system, that implies dependence of the vectors, of at least the one vector is dependent on the others from our discussion. So from this discussion, we notice one vector, at least one vector is depending on the others, means there is at least a trivial solution to the system. So because of that, we define linear independence as this one. That is a set of n vectors. The set of n vectors is said to be linearly independent, a linearly independent set. If this homogeneous system has only the trivial solution. Yeah, since we saw that non-trivial solution implies at least one vector is depending on the others, right? So this defines the linear independence. So it's reasonable that we give such a definition. So when we understand the definition, we can use it to check whether a set of vectors is a linearly independent set. So this definition also tells a method, because you just follow definition to check whether the set is a linearly independent set. Suppose you're given a number of vectors, you want to know if they are linearly independent. What we do is to solve a homogeneous system. For example, we solve this system and see if we have only trivial solution for the system. And if you prefer to use x1, that's fine. So if you put x1 instead of c1, c2, that's just another way to represent the same system, right? You can use that. So using that instead of those c1, c2. So again, same thing. See if the homogeneous system has only the trivial solution. So we can check independence of vectors using this definition. So here is a set of two vectors. So suppose you have v1, the first vector, second vector. See, those are just the names of concrete vectors. In this example, the first vector, second vector are given. And are they linearly independent or dependent? As a matter of fact, probably by observation, you notice that V2 is 3 times of V1. Because you see the V1, each entry times 3, you get V2. Yeah, so this V1, V2, you notice that relationship. So immediately you say, oh, V2 is representable as a linear combination of V1. So V2, so here we see that this is V2, which is 3 of V1. So V2 is dependent on V1. So the set is a linearly dependent set. Also, that shows that if I rewrite 3v1 minus v2 is 0, right? If I write this system in this homogeneous equation form, yeah, that's the vector form. 3v1 minus v2 is 0. So that means this system has a non-trivial solution. You see, this non-trivial solution means if I try to solve a homogeneous system, we know the system has at least a non-trivial solution. That means 3, -1 is a non-trivial solution. You see, when C1 is 3, when C2 is -1, that can make it 0, right? So that means this is a non-trivial solution to the homogeneous system. Yeah, so that by definition, we know if there are solutions more than trivial solutions, then it's not linearly independent. So that means whenever you notice a vector is a linear combination of other vectors in the set, then that implies you have a non-trivial solution to the homogeneous system. So that will not satisfy this. So it's not a linearly independent set. The two vectors are linearly dependent. And simply because the homogeneous system has non-trivial solutions. If you solve it, you can also try to solve it. Sometimes you do not immediately see a solution, whether there's a trivial solution or not. So we can just use our method, the augmented matrix for the homogeneous system. And if you reduce it to this form, this implies that we have a free variable, right? You can further reduce it if you want. You can scale the first rule by -1. So you reduce it all the way to the reduced echelon form. Immediately you see that C1 plus 3C C2, because we're solving for C1, C2. So based on the reduced echelon form, we know the equation, one equation has two variables. So there's one free variable. That means C2 is a free variable. So C1 can be anything as long as it's -3C2. And C2 is free, can be anything. So we know the C2, whenever C2 is non-zero, a solution set, when C2 is non-zero, then we have non-trivial solutions. So this means free variables, also implying non-trivial solutions for the homogeneous system. And that implies the two vectors are dependent. Okay, let's look at another example. Still two vectors. So if you see another set of two vectors, this time first vector, second vector, they are both in R3. That means vectors of 3 entries. Are they linearly dependent or independent? So if we use our definition, that means we want to check the first vector, second vector, we want to form the homogeneous system. This is the vector, right? Zero vector. So if we study this homogeneous system, do we have only trivial solutions? So this homogeneous system, it is the system in vector equation form. You see, put the first vector, second vector in vector equation form. You can also write the augmented matrix. So put the first vector, second vector right here, second vector, and the zero vector here. So we put augmented matrix because it's always easy to solve when you write, and then you solve it. Of course, when you solve, you want to reduce it so you can easily see whether we have only trivial solutions. So after you reduce, as we can see, this replacement of the second rule, right? The first rule times 2, twice the first row can be added to the second row, then that will result in a row of zeros. That means a free variable, right? Because the system is V1, V2, yeah, this system of this form. And that means the C1, if you scale one more time, so the first equation can be multiplied by -1. So then a row of 0, another row of 0, then we notice a free variable again. So what is the free variable? If you're solving this homogeneous system, then that means C1 minus 4, C2 is 0. So C2 can be anything. C2 is a free variable. So that means C1 is 4 C2, and C2 is free. So let's write so the C1, C2, if we look at solution to the system, C1 is 4 C2, and C2 can be still C2, anything you give to C2. So the C2 can be non-zero. When C2 is non-zero, then we have definitely non-trivial solutions. When C2 is 0, we have trivial solution, because we always have trivial solution for a homogeneous system. But when C2 is non-zero, then we have also non-trivial solutions. So immediately we conclude that the two vectors are linearly dependent, because the system has trivial solutions in addition to the non-trivial solutions. Has non-trivial solutions in addition to trivial solutions. Yeah, because trivial solution is always there, right, for any homogeneous system. So, okay, so you see the non-trivial solution of a homogeneous system implies linear dependence of vectors. If you have only trivial solutions for the homogeneous system, that means independence, linearly independent vectors. Okay, so now we go to some more examples. So it's very, like, once you go through a number of examples, you see how we apply definitions to check linear independence. So here I give you again V1, V2, two vectors. And the two vectors, if you want to determine if the set of two vectors, V1, V2, is a linearly independent set, what we do, we just solve a system. So put that's the system, right? We're trying to write the homogeneous system, see if we have only trivial solutions. If we immediately conclude that we have only trivial solution, then that means the two vectors are linearly independent. Otherwise, they are dependent. So the essential thing is to solve this for solutions, see if we have only trivial solutions. So to solve, it's straightforward. For homogeneous system, we know how to solve them. So just write the augmented matrix and do the row reductions. So you see the first vector here, second vector here. Yeah, so we just put coefficient matrix, right? And the right-hand side here. Certainly, you don't have to keep the column of zeros, as I remarked earlier. So right now, just for you to see, because that last column of zeros will stay as a column of zero no matter what elementary operation. So it will be reduced once we do replacement of the second rule. And then further, you can swap, right? Second with the third rule. So that will reduce it to -1, 4, 0. After we exchange the second and third rule, the two rules. Yeah, so then 0, 1, 0, and then a rule of 0. And then we can still do a little bit, one more step, because the first equation, we can scale it, multiply each entry by -1. So it becomes +1, -4, 0. So second rule is still the same as before. The third rule is a rule of zeros. And then now with this final form, so we're ready to look to decide. This is certainly a consistent system because any homogeneous system is consistent, right? We have at least a trivial solution. So remember that. So the question is, do we have only the trivial solution? So when you decide, you seek this reduced form tells, right? The first, that means the C1 minus the 4C2 is 0. The second one, it means the C2 is also 0. So that shows that the C2 has to be 0 from the second equation. And then if C2 is 0, then C1 has to be 0. So yes, we have only a trivial solution. For this homogeneous system, we have only trivial solution. What does that mean? That means the two vectors form a linearly independent set. So we have used the definition to check on the linear independence of two vectors. You can have more than two vectors. So when we have a set of three vectors, for example, here, specifically, first vector, second vector, third vector, and then can we check the linear independence of the three vectors? So we want to determine if the three vectors are linearly independent or not. So we need to write this form, right? We want to decide if the homogeneous system has only the trivial solution. So let's look at the homogeneous system. So since V1, V2, V3, and in front of each V vector, then we have the weight, right? That's the linear combination of the vectors equals a 0 vector. So we write the homogeneous system into a specific system, the vector equation form. This vector equation form, do we have only trivial solution? That is to be solved. We have to solve the homogeneous system to know whether we have only the trivial solution or not. So yeah, so by the way, we know the vector equation is the same as this two equations, right? 3x1, 6x2, 0x3 equals 0. That's the first. Second equation will be 1x1 times add 1x2 add 0x3 equals 0. That's the second equation. So it doesn't matter. It's just a quick review for you to realize again, the vector equation form, the equation involved with the variables, that kind of form. And also, yeah, when we solve it, so you can always use augmented matrix to reduce. But also reduce, you will easily discover that there is a non-trivial solution. Actually, by observation, we can make this non-zero. You see, if I put it 1 or 10, anything non-zero, right? If I make this one 0, x1 0, I can easily know that it is a non-trivial solution because 0 times this will be a 0 vector. That's a 0 vector. This one still 0 vector. So we can observe that if I give x1, x2, x3 of the system, if I make this one non-zero, and immediately if I make the other values 0, and immediately we find a solution to the homogeneous system. So even the x3, it doesn't have to be 1. It can be any non-zero value, right? So x3 can be any non-zero value. So for example, it can be a -1 or -10. Anything will work. So it's for our convenience, I just put a 1 to see at least there's one non-trivial solution. So that means trivial solution is not the only solution. So that means the 3 vectors are dependent because they're not independent. So quickly, so all this time we're using the definition to check linear independence. Definition says independent. The 3 vectors are linearly independent if and only if the system has only a trivial solution. That means whenever there's a non-trivial solution, the 3 vectors are not linearly independent. That means they're dependent when we have non-trivial solutions. Also, you notice from this example, we see whenever the set of vectors has a 0 vector, the set must be a linearly dependent set because this 0 vector, right, can be represented by other vectors. As we can see, anytime you have a set of vectors with a 0 vector as one vector in the set, then the 0 vector can easily represented by the other 2 vectors because v1, v2 here, as you can see, I can put a 0 times the first vector, 0 times the other vector, and this one with 1 of this 0 vector. So 0 vector is depending on other vectors. So as we can see, when this is a 1, then we can represent 0 vector in terms of other 2 vectors. So this is a property. If you, from this example, you can just remember that it is always true. We can generalize this result. That means if you have a set of vectors, if the set consists of 0 vector, then the set must be a linearly dependent set. Now we have set of vectors, and if you imagine the column vectors in a matrix, so here is a matrix. At boldface, the letter means this is a column vector. It's a vector. It's another column of the matrix, the second column. Here is the last column of the matrix. As you can see, had boldface each letter just to indicate that's a vector, a column vector. So we have n columns for this matrix. And if we want to know whether the n columns of the matrix are linearly independent, then what we do, we just do the same because they're just vectors, right? To determine the linear independence of the n vectors is just to study this homogeneous system. This is the vector equation. Yeah, so each vector is the column of the matrix. So you just write the vector equation, see if the homogeneous system has only a trivial solution. If this implies only a trivial solution, then we know that the columns of the matrix are linearly independent. Otherwise, they are linearly dependent. So let's recall that vector equation is the same as this matrix equation, right? So this is just A with each column written here. So that's just the matrix A times X equals 0. So it doesn't matter if you use a matrix equation, same. So I just want you to recognize the equivalence. That means no matter you use the vector equation to study the columns of A or the matrix equation, A times the X equals 0. Here, A is this one. The X is the column vector. Yeah, 0 is the right-hand side. So that's the matrix equation, right? Or this one. So they're the same matrix equation or vector equation. They're the same linear system. So either form, you can use either form. So as long as you solve this system and you want to discover whether X is the only trivial solution. If X being 0, the system has only the trivial solution, then that means the columns of the matrix are linearly independent. Otherwise, they're dependent. So let's look at the matrix. So here is a given matrix A with 3 columns. We want to determine if the columns of this matrix A, right? We have 3 columns, column A1, A2, the second column, A3, the third column of A. Are they all linearly independent? So what we can do is to write the homogeneous system using the 3 columns. So just to examine this, you see the first column of A here, second column of A here, third column of A here. So we write the system, homogeneous system, and try to decide if the homogeneous system has only a trivial solution. So we need to solve for x1, x2, x3, the weights of the vectors. So solve it, then, of course, if you write immediately this A into the, using this A, we can also write the same system, right? Into A, x equals 0, the matrix equation form. Yeah. So this is just the recognize the equivalent forms. So this A, this is the AX equal 0, or this vector equation form. They are the same. So either one you can choose. So we solve this homogeneous system, and then what do we find? So after you reduce the augmented matrix, we notice this is the reduced augmented matrix. And that means first equation x1 minus 5x3. The second equation is x2 minus 1x3 equals 0. So with that, we notice a free variable. So that means x1 is 5x3, x2 is x3. x3 can be anything, just a free variable. So what we have done is to solve the homogeneous system, we discovered that general solution for the system. So the x1 is 5x3, x2 is 1x3, x3 is x3 because x3 is a free variable. So immediately we notice non-trivial solutions, right? So non-trivial solution, when x3 is not 0, then we have a non-trivial solution. So this, So when x3 is not 0, then at least the one of the entries will be non-zero. So as long as the one entry is non-zero, already enough to say it's a non-trivial solution. So we have a linearly dependent set of columns. So the 3 columns are linearly dependent because the homogeneous system has non-trivial solutions. Yeah, that means whenever there's a free variable, you know there's definitely more than trivial solutions. Yeah. So whenever there's a free variable, so sometimes it's easier to tell if there's a free variable. If you have a matrix with 3 columns, and we don't have to reduce, we know there must be at least one free variable, right? Because you notice 2 equations, 3 variables. So from these 2 equations, we notice that x1, x2 can be represented in terms of this x3. So this homogeneous system, which is same as this, there is a free variable. And you notice that, 2 constraints, that means 2 equations, but you have 3 variables. There must be a free variable, at least one free variable. That means this homogeneous system with the given A being that one, the columns of A are dependent. Yeah, because we have non-trivial solutions. With the free variable, we have definitely non-trivial solutions. So let's look at another matrix. This matrix, if we look at this matrix, we want to know the columns, how many columns do you see? 1 column, 2nd column, 3rd column, 4th column, 5th. 5 columns. Are these 5 columns linearly independent? What do? We just solve the homogeneous system, see if we have only a trivial solution. So once we solve, you think 3, there must be at least 2 free variables, maybe even more. So we know we have 3 equations, 5 variables in this. Because when we solve this as a linear combination of columns of the A. And we know that A, x1, x2, x3, x4, x5. So this, the AX equals 0, which is another on the right-hand side. So the X is a vector of 5 entries. So when you solve this homogeneous system of 3 equations with 5 variables, there must be at least 2 free variables. Maybe could be more, depending on how it is, what the matrix A is reduced to. So, but we know at least, yeah, there must be free variables. Therefore, we must have non-trivial solutions. So if this homogeneous system has non-trivial solutions, then the columns of A are linearly dependent. So here we want to see a very important thing, that is, in this matrix, we notice how many columns? 5 columns. And so when we study this, we have 3 equations only. So when you have more columns than equations, then the system has some free variables, implying linear dependence of the columns of A. That also means when we have whenever you have more vectors than the number of entries. So if we compare, each vector has 3 entries, right? 3 entries. So if you have more vectors in the homogeneous system, these vectors must be dependent. Yeah, they're linearly dependent. Whenever you have, suppose let's use n as the number of vectors. Let's use m, because m means the number of entries in each vector. So here n is 5. That's the total number of vectors. And each vector, so we have v1, v2, v5. That's the total number of vectors in the set. But n, the m is the dimension. So each vector is in R3, right? In that means number of entries of each vector is 3 entries. So if n is bigger than m, which is 3 here, then the set must be linearly dependent set. So that's another property which is always true, because we can always write the homogeneous system such as this kind. When you have more vectors, if your number of vectors in the set is greater than the number of entries in each vector, then this set of vectors will be a linearly dependent set. Okay, it's all because of the homogeneous system. The corresponding homogeneous system has free variables, right? When you have more vectors, then you will certainly have some free variables, because you have less equations than variables. You must have free variables. That means you must have non-trivial solutions. So that's a discussion on the linear independence or versus dependence of vectors. These vectors could be columns of a certain matrix.